Thank you so much for the introduction. So I realized this morning when John gave his talk that I believe my presentation now will be an example of, or an illustration of the main takeaways from his talk. He said that, okay, you can do amazing things with logic-based Benders decomposition. You can solve really large-scale challenging problems, but you have to adopt what you do to your problem. So you can consider my presentation an illustration of that. So what I want to do is to talk a bit in general to set the stage for the things that I need for my application. And then I will introduce the application, and connecting to what Karen said, if these guys, she talked about discovered complexity in the 60s. The company I worked with, they understood what that meant when we did this project. They wanted to solve a really large scale problem. And then as a final note, I will introduce a new acceleration technique that we used to improve the results even further in this project. So, and I mean, back to the things that most of you have said already. I mean, using logic-based Benders decomposition is an opportunity to exploit problem structure in a good way. But if you compare to, I think there's a difference when you use Danzig-Wolff decomposition. Then you get a lot for free by just making the decomposition. You get a stronger formulation, for example. But here you really have to work with the acceleration techniques to have the speed-ups that you need. So, as I said when I introduced this, I will try to give some experience from exploiting problem structure in practice and this design of acceleration techniques. So a typical problem structure would be that we have some strategic decisions to assign jobs to factories or machines maybe. And then we have some remaining decisions. We want to schedule these jobs at the factories. And you cannot make these decisions independent of each other because they are connected. If you want to minimize the make span, for example, the make span you can get at each factory depends on the assignment of jobs that you did. And also when you make this, typically in this setting, when you make these strategic decisions, you have some constraints on the remaining decisions. And in this setting, we think about, I mean, you can do this in, it's more general, like John also said, but we will think about this in a setting where both levels of decisions are discrete and you have NP-hard problems. So you've seen this basic scheme many times today, but I will repeat it. So if you think about the most basic setting you can have, instead of the complete model for your problem with all the decisions and constraints, you have your master problem that you get from this complete model by relaxing some aspects of these remaining decisions. And then you have a subproblem that you obtain from this complete model for a fixed choice of strategic decisions. And then this subproblem is designed to detect infeasibility or non-optimality for your complete problem. So then you get a solution scheme that looks something like this. The problem structure and notation that I will use looks like this. So, and I will have X as my master problem variables to shift back from the previous speaker to keep you awake. And also, I will think about this as a setting where I would have a MIP formulation with respect to X and a CP formulation with respect to Y. And this is also, this influences my notation a bit. I will work with binary master problem variables and an objective that most of the time only depends on the X decisions. And of course, then we will have some constraints with respect to the X variables only and with the Y variables only, and then some constraints that connects them. So for the master problem, it would be looks like this. And then I will add my feasibility cuts. I have a solution in iteration k. I use that to fix xk and get my subproblem. And in this case, since my objective only depends on x, I have a feasibility subproblem. And if this subproblem turns out to be infeasible, I will exclude the current solution from the master problem by a feasibility cut, a no-good cut on this form. And this is what I have for my basic scheme. So then it looks something like this. Master problem, feasible solution, If the subproblem is infeasible, I return a cut to the master problem. And the only ways I can end this loop is either I get an infeasible master problem, because then, since this is a relaxation of my original problem, I can conclude that my problem is infeasible. Also, if my subproblem turns out to be feasible, then I know I have an optimal solution. But just like most of you have indicated already today, if I would only do this very basic scheme, I would have a poor computational performance. So these acceleration techniques, they are really important. And we have some examples. We can try to strengthen the master problem. Maybe there is some information from the subproblem that we should take into account also in our master problem. In the example with the factories, maybe I can derive a bound on how many jobs I should assign to each factory, and that can help the master problem making better decisions. We can do cut strengthening, which I will get back to. We can do analytic cuts, like John mentioned, to use what we know about the problem structure to formulate better cuts. And of course, we can plug in heuristics in a good way somewhere. And these are typically tailored to the problem structure. But I'm interested in one structure that you see in a lot of these problems. So if you have a connection between the x and the y variables, where assigning x equal to 1 is the only thing that implies a restriction in your problem with respect to y, then you can use rather generic search strategies. And I will illustrate this by an example. If we go back to our factory example here, and I would say that the most general no-good cut you can have for that one looks like this. But for this example, that means for each job we make 3 decisions. We say, okay, we assign this job to the green factory, and we do not assign it to the red one, and we do not assign it to the blue one. But not assigning it to the red one, it doesn't do anything to this problem. The red problem doesn't care about a job not being assigned there, right? So, but it matters for the green factory. So the only decisions that matters here are the ones that are assignments. And if you have a structure like this, I would say that it's only the x equal to 1 decision that implies a restriction on y. Then you don't need to care about the 0 decisions when you return your cut. So then you have a structure that looks like this. And if you have this type of structure, that also means that if you have a variable assigned to the value 1 and then you change it into a 0, that will give you a relaxation. So that means you remove 1 job here. That's a relaxation of that subproblem. And if you have this structure, then you can strengthen your cuts by finding subsets that causes infeasibility. So let's say again now that the green factory here, assigning these 4 jobs, you conclude that, okay, the subproblem is infeasible, I should return a cut. But maybe the cause of the infeasibility is the combination of these 2 jobs. So then that's a stronger information to return to your master problem. And then you want to do this. And if you want to find such a subset, you can apply any of your favorite search strategies for this. You want to find a subset that gives you an infeasible subproblem. And there are different versions of this. And the only thing you need to do is to search and find if, okay, I want to study this particular subset, then you solve the pricing problem for that and see what happens. There are 2 types of strategies. Some of them, they will return what is called an irreducible cut, which means that with the cut that you have, there's no single variable you can put to 0 and get still have an infeasible solution. So like a local optima. And some, like the greedy search, they can return cuts that are not irreducible. And we did some work on trying to give a joint description of these and also do some computational evaluations. And we started off with a previous PhD student of mine, Emil, to look at feasibility cuts. And there we had several types of problems and instances and so on. And there it was rather clear to conclude that you should always go for the irreducible cuts. It pays off to invest in that. And then this work was continued together with Steve and his PhD student Agrim, and then we also added value cuts to this evaluation. And I won't go through the details here. If someone would be interested in having some ideas on what seems to work and so on, you can check the papers. I realized also, we have one speaker after me, but this far no one has mentioned learning yet, together with Bender's decomposition. So, but I have one slide about this. So if we are in this setting, and we want to find these subsets that gives us the really good cuts. So one way to combine Bender's decomposition with learning would be to try to predict a subset that gives an irreducible cut. That would be ideal, right? Of course, it's a difficult learning task, but you can try to find a promising set, and then you can still apply the strengthening and also extend the set if you needed to find a good cut. And that can reduce the number of subproblems that you want to solve. And we've made an implementation of this where we had like an autoregressive approach where we had a learn function that looks at the current subset and see, okay, which variable is promising to add. And also an indicator saying, okay, this seems to be enough. And in this work, the main author is Johannes Varga. And he's a PhD student with Günther Reidel in Vienna. And the results indicate, okay, we can reduce the number of subproblems to solve, but I think it should be possible to improve on these results quite a lot. And if anyone would be interested in the instances and code we have for this, please reach out to me because it's available for anyone who wants to improve this. So, like, this is the background I think that we need before turning to the application. So the application here is electronics in aircraft. So imagine a whole aircraft and all the electronic that goes into this aircraft. And sensors that collect information, units that process the information, actuators that control the aircraft, and also equipment like screens presenting information to the pilot. And an aircraft is a safety critical system, so everything needs to be done in the right way. You can't have the situation with your PC, oh, suddenly something stalls. I mean, if you're a pilot and want to pull down the landing gear, it has to happen, and it has to happen every time. So the way that you design these systems are rather different from your laptop. And I don't have time to go into the engineering background on this, so I will just present the optimization problem today. But what we need to know is that one of the things that they do to have this perfect performance is that they schedule down to the nanosecond everything that's allowed to happen in the system. Of course, the data and the computations will change, but the resources are already allocated when you compile the system and plug it into the plane. So the problem formulation looks like this. So we have here a communication network, an Ethernet, with a very special communication protocol. And this is used to communicate between nodes. And in each of the nodes, you have several processors. So you have one, the communication module, that's in charge of everything that has to do with the communication, sending messages on the network, communicating with the application modules, one or several, in each node. And these communication modules, they are really the busy guys because everything has to pass through them. What we want to do is to create a cyclic schedule for all of these processors and the communication network. And this cycle is only 1 second long. So it's a super short schedule until you realize that electronics lives in the world of nanoseconds. So that's a very long schedule, 10 to the power of 9. And what's also important to know when we think about the solution method for this is that we want to find a feasible schedule. We don't have an objective at all. I tried to find some objective, but they only say it's a feasibility problem or deduce that no solution exists. And it seems like they are always on this like borderline between feasibility and infeasibility. So we really need to be careful and say, okay, now we have a feasible solution, everyone's happy. But if we cannot find a feasible solution, we need to like also provide a proof of that. Because if I tell this aircraft manufacturer that, sorry, you need to buy new hardware, that costs millions and millions and millions. So you don't want to do that unless it's necessary. So when we think about this from like try to categorize this a bit, it's a multiprocessor scheduling where you have periodic tasks. And on these application modules, you have rather few tasks, and they are very long. And you have several instances per major frame, so they are scheduled several times per second. And then on your communication modules, you have a huge number of tasks, but they are only scheduled once per second. And they are also much, much shorter. And then we have what is called dependencies. And these are simply precedence relations with time lags, but in a cyclical manner, because it's repeated all the time. And you can have these dependencies on the same or on different modules. But what you simply need to do for these modules is that you want to sequence the tasks and assign a start time to each task. So task scheduling and communication messages. So when we want to schedule, I will explain this communication scheduling through examples. So we can consider this as a timeline on our communication network, and then we have a sending communication module and a receiving one. And this is defined in a way so that you have time slots where you can send the messages. To schedule these, it means that you put a message in a discrete time slot. But from a technical perspective, to be able to send this message, you have several things that needs to happen. You need to prepare, send, dequeue, and then read the message. So these are tasks involved in making this happen. And these tasks are all restricted by dependencies related to this. But the actual decision is rather easy. You need to choose a time slot and assign to this time slot. The complicated part is that the choice of time slot has an influence on the involved tasks. And I will illustrate this also by an example. So if I put a message here, that means I will have some restrictions on the release time and deadlines of these tasks. That's one thing that happens. Also, if we look at an example with two messages, the order of the messages will also give additional restrictions on the order of these tasks. So if I put the message here, then I know this task must happen before that one. For these ones, it doesn't matter, but for these ones. And also for the queuing part here, that also has to be made in the same order. And those are simply technical restrictions on the electronics. The really nasty part is you can put several messages in the same slot. And what happens then is that you merge the tasks. And that's a good thing because that saves you resources. So this is an important decision to make. So if I would send the two messages in the same slot, that means that these two tasks are completely merged, because then this can be done at the same time. And for these, you save some resources. They are not completely merged, but you save some resources, and that's the same for these. So this means that this connection is rather intricate. And before moving on to how to solve this problem, I want to show you an instance of practical relevance. Fortunately, it took me a while to understand that this was what they wanted to do, because we had to formulate the problem first. If I would have known in advance, I would have said no, I think. So on this communication network, it's almost 4,000 messages to schedule, and that's okay. If we look at the different nodes, in the red boxes we have the application modules. So here we have 14 tasks scheduled 64 times on this application module, and here it's 2 application modules with just 4 tasks each, and so on. But the real challenge are in these communication modules. So if we look at this single processor here, we have over 16,000 tasks. And then we should also remember all of these things that happens when we assign the messages. So this is really this is the one of the main challenges here. So we need to go large scale. And so when we realized, okay, this is the problem, and then they said, oh, but we also have a toy instance. Oh, great. And this looked something like this. Only 64 messages, some 1,000 tasks here, and so on. And we were thinking, okay, let's try to formulate a MIP model and try to solve it. We did the best we could to improve it, use the tricks that we know. But if we ran it for a week, we had no feasible solution. And I think we also ran it for 2 weeks, but nothing happens at all in a MIP solver. And then I took some help from some constraint programming friends. We had a master thesis together and tried to solve the problem, but we couldn't. So this was sort of the starting point. So, but then we had to like take a step back and try to understand, okay, what kind of creature is this and how should we handle it? And as I already indicated, this interaction between the task and the communication scheduling is challenging. It's a messy part of the model, since we have this impact on the task scheduling. But another challenge is this sequencing. So if we try to like think about what kind of formulation we can have, if we have more than 15,000 tasks on a single module, that gives us, if you think about this in a disjunctive sense, we have about 100 million task I before j decisions, and that's a lot. And then you can think, oh, but some time index formulation, but that's even worse because we have nanoseconds, so that would be something like 10 to the power of 12 decisions. So the magnitude is not on our side here. But there are also some good news. So, I mean, the only thing we need to do is to find a feasible schedule or prove that none exists. We don't have an objective to care about. We know what, like, okay, the challenge is in this interaction. When it comes to the sequencing, I'm from the MIP side of things, so I tend to think about that type of modeling. But yeah, talking to the constraint programming friends, okay, these solvers are better equipped for this type of sequencing, and especially IBM's CPO turned out to be the right choice. So there is some problem structure to exploit here. And what I would say is a promising type of decomposition scheme would be something like this, some pre-processing, solve a relaxed problem. Now we're back to the idea that, okay, we should prove infeasibility or find a schedule. So, because if we can have this relaxed problem helping us to prove infeasibility, that's a good thing, right? And then we can restrict the solution space, solve a subproblem. Oh, if we find a schedule, then we're happy. Otherwise, we can add some information back to our relaxed problem. And we actually made two versions of this. And I will get back to those. Starting first with some ideas for how to do the decomposition. So if we look at the sequencing of the tasks, I will do this also by an example. If in this illustration here, I have the release time and deadlines of these tasks. But if you look at the technical restrictions with lots of different things, you can do some pre-processing in the sense that you do propagation in constraint programming. So you can conclude that only some of these subintervals are actually feasible in a solution. So you can remove parts of this interval. And this is something that we can use. If we would go back to think about this in the sense of task I before j decisions, just to understand the impact of having these smaller subintervals, if I would have these smaller subintervals, that would give me a reduction of about a factor of 10 when I consider these subintervals. And if I would fix an assignment of the subintervals, that's another factor of 10. So things really happen when you create the subintervals, if you use this in the pre-processing and reduce the number of variables and so on. And for a fixed assignment, something also happens. So in this model, we have like a hierarchy of decisions. I haven't talked much about the application modules, but these are the ones with the huge tasks. So these are really strategic decisions that makes a huge impact on the solution space. So you need to like always allow you to change these decisions. The message to slot assignments, that's like a messy and part of the model, and it has a large impact on the remaining structure if you can fix those decisions. If you assign tasks to intervals on these communication modules, it reduces the solution space with these intervals that I showed you. So if you can make good decisions there, then you can reduce your problem quite a lot. And what remains then is this sequencing of tasks. But that's a rather well-known structure, so there's more to use there. So I will now present two decomposition approaches. One of them is logic-based Bender's decomposition. But the only difference between them, or the difference between them, is the decisions that we put in the master problem and the subproblem, and the type of feedback information. So the difference is on this line here. So, and this first one, I won't talk about the details here because I will only use it for comparison. But here we keep more decisions in the master problem, essentially. So what we do is we place tasks in subintervals and messages in slots, and this gives us a rather messy model that we can solve by Gurobi. Then we get a subproblem where we sequence tasks, but they are already placed in these subintervals. And then what we return back as information is tasks that we want to make part of the master problem. So then we sequence some of the tasks also in the master problem. So this is a pure MIP approach, and think about like constraint generation in general. And mainly we use this to detect infeasibility. The other part that I'm going to spend a bit more time on is the logic-based Bender's decomposition. Here we assign messages to slots, but we do not assign tasks to intervals, and this gives still a rather messy master problem, I would say, but it's not challenging to solve. So Gurobi can solve this rather quickly. And for our subproblem, we want to sequence the tasks. They are not placed in these subintervals. We don't have an objective. We use IBM elog CP optimizer, and our feedback mechanisms are these no-good cuts. So here, this master problem is very unlikely to detect infeasibility. That is something that we know from our tests because it's a more relaxed problem. But it helps us finding a feasible schedule faster if it exists. So a first computational comparison. We had a set of public instances. This is the largest set that we have among the public ones. And then we compare these two decomposition approaches. For the first one, we had to use the fat nodes on the cluster because they require quite a lot of memory. The second decomposition approach does not. So it's not really a fair comparison in that sense. But the results look something like this. So if we look at the first decomposition approach, I will use these diagrams with time here. So we have a solution time of 70 hours. And then these are the number of solved instances. And if you look at the decomposition approach 1, it took over 30 hours before the first instance was solved at all. But then for this part, we also integrated some adaptive large neighborhood search that could really help us to improve the results. So if we have 70 hours, then we solve almost all the instances there. But then if we look at the results from the logic-based Bender's decomposition, we can see that something happens, like relating to what Steve said. Okay, this looks promising. We should investigate this further. I mean, the blue line here was, okay, the first step to see, okay, it seems to work for at least the easiest ones. And after doing some work on the cut strengthening, we could also solve even more problems like this. But you see that it flattens out here. And then we were back to the drawing board, like in Steve's iterations. Okay, what should we do to improve these results? It's promising, but we're not really there. And that takes me to the final part of the presentation about a partial assignment acceleration technique. So this work covers two questions, I would say. What we use in this application is only the second one, but I will introduce both because there's some symmetry to it. Now we need to go back to the first part of the presentation and remember what was said then, that we do these searches over subsets of variables when we have this nice implication structure. Then we can do these searches for subsets and return stronger cuts. But what happens if we don't have, maybe we almost have this nice implication structure, but something that makes it not work? So can we generalize this a bit if we still want to use these search techniques? And also, can we use the search that we do to strengthen our cuts to also find feasible solutions? because that's a way to improve the primal bound as we go along. So the way to achieve this is to view the subproblem in a slightly different way to start with. So when I gave you the subproblem the first time, I simply took the original model, fixed x, and then removed everything that has to do with x. But instead, I will keep the original model like this, and I will put this assignment here to say, okay, x has to equal x bar. And if I say that this needs to hold for all the master problem variables, I have the same behavior as in my subproblem, that, okay, if this problem is infeasible, I get a cut. If it's feasible, I get a feasible solution. What I can do then is to say, okay, but if I take a subset instead, then the same thing will hold, right? Like in the cut strengthening. But now I have this as an explicit assignment here. But of course, there was a reason we wanted to do the decomposition in the first place, because if I do it like this, I completely destroy the structure. So we cannot really do this in practice, but it's a starting point. So instead, to find cuts, then I can make a relaxation of the problem in a way that's subset consistent, meaning that if I have two subsets and look at their respective relaxations, if this one is a subset of this one, this problem needs to be a relaxation of this one. And do it in a way so that I get a nice subproblem structure. And this is like the property you get for free in the implication case, I would say. And then I can do the same thing for finding feasible solutions. I can take this partial assignment problem, I can make a restriction in the same subset consistent way, do it in a way that I get a nice subproblem structure, and then if I solve this problem and find a feasible solution, then I'm happy. So the illustration looks like this. So if we look at the partial assignment subproblem, this first version, if I solve it and I get a feasible solution, I have a feasible solution. If it's infeasible, I have a cut. But this is something I don't want to do in practice. So instead here, I introduce a relaxation so that I get something that's easy to solve. And if this relaxation is infeasible, then I still have a cut. The cost of doing this is that if this relaxation turns out to be feasible, then I don't know anything. I cannot conclude anything from that. Also, on the other end, I introduce a restriction. If the restriction turns out to be feasible, I can use that solution. But if the restriction is infeasible, then I don't know anything. So, but this is something that I might be able to use in my method. So the way that we did this was to include it as an additional step in our cut strengthening. So we also, instead of just solving the problem for these subsets to find cuts, we also solve these restrictions to find feasible solutions. And we did it in this way. So if the relaxation is feasible, then we try also with the restriction. And if the relaxation is infeasible, then we try with the complement instead. And then, of course, you need to update all the details of the cut strengthening to make this work, but that's more technical details, I would say. And the result of doing this is the improvement that we were hoping for, almost. You can tell that within 70 hours we solved all instances but one. So for that long solution time, it didn't matter, but you can tell here is the practical difference. So most of the problems are solved within 24 hours now, and that's an okay result in this context. We are working on the development of a whole aircraft, so that's okay. So just concluding with some acknowledgements. Thank you so much for listening.